use about the same number of barrels of petroleum per year. Since 81 to 2001, it's hardly changed at all. Well, what that means is this means you need between 60 and 80% more liquid energy, more barrels of petroleum to meet the demand 15 years out from now. And on the electricity side, we've actually seen an increase in how much is used per capita. So that means we need as much as 100% more electricity and 75% more. So what we've got is large expansions in demand coupled with higher cost. And what that means is if you're going into the energy business, you can probably make more money in the future than people have made in the past. It also means that there's going to be a search for substitutes. We gotta find different ways to do it. So even just on the energy side, if energy prices become more dear, that means that we have greater potential to go ahead and develop bioenergy or wind energy or energy from the ocean or whatever form of energy that you might be interested in. Now there's another part of this story, and that's the greenhouse gas story. I do quite a bit of work on this, so I'm just going to pull a few slides up from various sources and talk to you about the greenhouse gas part of this. This is the pace of climate change. Now, this red line here is a 150-year trend line, and that particular line raises 1/100th of a degree per decade. Well, no, I'm sorry, 0.05, so 1/20th of a degree per decade. So on average, the last 150 years, we've gone up about a 1/20th of a degree per decade. That amounts over 150 years, and this is degrees centigrade, to about a 1 degree centigrade change over that whole time period. However, if we look at the last 100 years, that rate goes up from 1/2 degree to 3/4 of a degree. If we look at the last 50 years, the rate basically triples off the 150 year to about, what's that, 1/8 of a degree per decade. And nowadays we're running close to 2/10 of a degree in the last 25 years. Last year was the warmest year in recorded history. 19 of the 20 warmest years in recorded history have been in the last 20 years. So we have an accelerating temperature change that we're observing. What a lot of people say the underlying cause is carbon dioxide. I started working on climate change in 1985. Probably most of you were born after 19. No, you got to be born by 1985. No? Oh well.
I was born in
That's right. That means you're 25. So most of you are. I started doing this before you were even a gleam in your parents' eye. At that point, we talked about 340 parts per million or so as the atmospheric carbon dioxide concentration. This year in May, we hit 395. So we went up 55 points on atmospheric carbon dioxide concentration in a 25-year period, about 2 points per year, or what's that, 16%, or a fairly large number. Apparently, and I've never done the calculation on this, that's about equivalent to putting a lake of carbon dioxide in the atmosphere the size of the Gulf of Mexico. When you burn coal, 99% of the carbon in it is released in the form of carbon dioxide. Same sorts of things happens on the petroleum side. The greenhouse gas theory is that putting all that stuff up there causes a reflection in solar radiation. Solar radiation punches in from the sun, it hits the Earth's surface, It reflects off the Earth's surface and goes back out into space. But if you put some reflective surface up here, what happens is the radiation that would ordinarily be reflected back out into space, some of it is being trapped and held in the Earth's system. One time I had to go to the greenhouses on a day it was 30 degrees. The one over by Reed Arena, it was at least 80 in those greenhouses. I mean, what's happening there is the sun punches through, it hits the white surface in the greenhouse, starts to take off back out, but the glass reflects it back in. This is just a mini case of this, this greenhouse effect. Now, this is observations based on satellite measurements of the radiation reflected off the Earth's surface. This blue line here is what you're supposed to see, according to theory. You know, this distribution of wavelengths of light. This red line is what we do see. Notice there's a big hole in it here. That's the bands of radiation that would be trapped by carbon dioxide. So what we're seeing is a verification that not as much is reflecting off as what would normally happen. This is the methane band, this is the nitrous oxide band. We can see trapping of this radiation in these three levels, and it's leading to this heat buildup. So if somebody comes at you and starts saying it's volcanic vents or it's sunspots, or I don't think so. Yeah.
Quick question: if this is a snapshot, do you know when that was taken? What year? 'Cause it'd be interesting to see if.
I've tried to get a time series of these, but so far I've been unsuccessful.
Okay.
The problem is that nobody in the 1850s put up satellites. So where do these emissions come from of carbon dioxide? And you probably know this, but carbon dioxide is a greenhouse gas that they have this sort of set of relative measures of how much heat it traps. 1 ton of carbon dioxide traps 1 unit of heat. A ton of methane traps, depending on which numbers you use, between 21 and 24. A ton of nitrous oxide traps between 296 and 310 tons. And then there's some stuff like air conditioning chemicals, SF6s and some of that, that'll trap 4,000 ton equivalent of carbon dioxide. So the emissions are not all created equal in this regard. Some are more severe than others. This is the picture in carbon dioxide equivalents. About 60% globally of our emissions come from fossil fuel consumption. In the United States, that number is about 84%. It's about 42% from coal, about 42% from petroleum. So energy is one of the big factors where a lot of these emissions are coming from. There's also a substantial amount from agriculture and forestry on a global basis, about 30%. This 17% here from forestry is mainly from tropical deforestation. When we cut down rainforest, it contains a tremendous amount of carbon, and that's that. Agriculture, this is animals and rice. New Zealand, the largest component of its greenhouse gas inventory is from cattle and sheep, doing something called enteric fermentation, which some of you may know what it means. I never thought I'd work on it. It means animals belching and releasing gas in other places. So here we've got some fairly substantial agricultural contributions, but the rest of this is energy, transport, industry, housing, those sorts of things. What this means is greenhouse gases are going to put pressure. If we want to control greenhouse gases, that's going to put pressure on the energy industry. And there's a couple of things you can do. You can use a renewable energy source, which I'll talk about here, or you can do what we call carbon capture and storage. Anybody know what that is? I mean, what you're trying to do is catch carbon dioxide as it's coming out the flue gases from an electrical power plant and then injecting it underground, but that's relatively expensive. Also, it's hard to do with an automobile because who's going to run around with a baggie on the tailpipe trying to catch the gases as they're coming out. Bioenergy gets us into the carbon recycling business. In particular, as trees and plants grow through photosynthesis, they take carbon dioxide out of the atmosphere, respire the oxygen, and store the carbon in the roots and in the standing body of the trees. When we burn them, say in an electrical power plant, they also release 99% of that carbon, but it's recycling carbon that they sucked out of the atmosphere. So if you can use wood instead of using coal or petroleum, you're recycling as opposed to on net adding. Coal is ultimately plant material, but it's been buried for millions of years, and when you burn it, you're just contributing that much more new stuff to the atmosphere. There are, though, some elements where this isn't 100% recycling. You make nitrogen fertilizer out of natural gas, you release the carbon when you're doing that, so you get emissions due to driving trucks around, applying fertilizer and pesticides. You get emissions when you're hauling this stuff. One time I saw a picture of how much switchgrass it took to run an electrical power plant for 15 minutes, and it looked about as big as this building. I mean, there was a guy standing in front of it, and it was much larger than that guy, much wider, much deeper. So it's a big logistical and hauling problem. And then it takes energy to convert these things, like pyrolysis. To heat something to 3,000 degrees, you're going to have to apply energy to get there. We do something called life cycle accounting on this, where what we try to take a look at is how, in effect, it's the energy in to energy out ratio, although it's the carbon in to carbon out. And notice corn ethanol, which we're now making, is somewhere in the 25% to 30% range efficient, meaning you emit about 75% as much in the processing, production, and hauling as the energy value you get from it. The cellulosic ethanols look like they're going to be a little bit better, 70% or quite a bit better. But on the other hand, electricity, where you're burning wood, is more in the 90% efficient rate. So there's some real trade-offs here, and this is why I said early on, if you're really after greenhouse gases, maybe electricity is where you ought to go. If you couple this with carbon